Okay, so this one comes out to 8.567. Close.
Is entropy absolute value?
Entropies are absolute entropies off the table.
So,
But they aren't absolute values. You just take it as
because when I took E69 something subtract to 188, I get a negative number. So we just keep it as a positive number.
no. If it comes out negative, it should be negative. This cannot be negative because it's going from a liquid to a gas. Entropy is increasing, so it's got to be positive. And so let's take a look at the numbers here. Again, if we have H2O gas is 188.8 minus 69.9, it's going to give you a positive number. All right, so they're supposed to be the same. They came out close, so we're okay. Right? Sometimes they're going to come out different because of rounding or because of experimental error, but these came out okay. All right. But what this says is this. This says the Q. I already know what my Q is. What is my Q for this? The Q is, well, we got, it's going to be, another, well, if we have a positive delta G, what does that tell you? It's non-spontaneous under the conditions given. So under the conditions given, which is the temperature's at 298, and this is under standard conditions, it's non-spontaneous. Well, what are standard conditions? Standard conditions are gases are at 1 bar, 1 atmosphere, and the solutions are at 1 molar. And so what this is telling me is this. At room temperature, I cannot sustain the pressure of water 1 atmosphere. In other words, you know, what's the humidity today? You know, the humidity is less than 100%, right? But do you know, at 100% humidity, that's what we call the vapor pressure of water. And the vapor pressure of water at 25 degrees C is like around 25 millimeters of mercury, right? 25 millimeters of mercury, is that anywhere near 1 atmosphere, 760 millimeters of mercury? No. And so if this room were saturated with water vapor, it would be 100% humidity, which is about 25 millimeters of mercury. Well, here we're trying to put 760 millimeters of mercury of water vapor in this room. Is that sustainable? No, that's not sustainable. In other words, here, this is non-spontaneous. Q, I know that Q is 1 under standard conditions. Q's got to be 1 because, well, Q is going to equal the activity of H2O gas raised to the first power divided by the activity of H2O liquid raised to the first power. The activity of H2O gas is just the pressure of H2O vapor divided by 1 here. So this is just the pressure of H2O. And so we can't sustain a vapor pressure of water here at of 1 atmosphere or 1 bar at room temperature. And so, in other words, Q is, in this case, Q is greater than K, so we have to have the reverse happen. In other words, we need some of this water vapor to condense into liquid. We've got too much water vapor in the air. All right, so it's non-spontaneous, but can we make it spontaneous? Is there a way to force more water vapor into the air? Yeah, as you recall, do you guys remember the vapor pressure curve of water? we can increase the vapor pressure of water by increasing its temperature. And that way we could sustain more water. In other words, can we make the boiling of water spontaneous under standard conditions? We could if we change the temperature. Because I know, do you know the normal boiling point? The normal boiling point is when the pressure of the water equals 1 atmosphere. The normal boiling point is the temperature. And so the normal boiling point of water is 373 Kelvin. At 373 Kelvin, the vapor pressure of water should be 1 atmosphere. And so the vapor pressure of water, if it's 1 atmosphere, matches atmospheric pressure, normal atmospheric pressure, and we have boiling occur. And so one of the things I could do with this particular process here is to make it spontaneous at a temperature other than 298. And so this is at 298 Kelvin. I can calculate it at any other temperature, but what I want to do is I want to figure out at what temperature will this go from non-spontaneous to spontaneous. And so that will be the next calculation here. In other words, we want K equals 1. So at what temperature will K equal 1? But we'll talk about that more later. What temperature will it go spontaneous? So we're trying to solve for the temperature under standard conditions. So under standard conditions, we want delta G naught at temperature T is equal to delta H naught at temperature T minus T delta S naught at temperature T. We're going to assume that the enthalpy change at 298 doesn't change much with temperature, and the same thing. That is, whatever temperature we have, the enthalpy and the entropy change should be about the same as the one at 298 Kelvin. So right now, the delta G naught is plus 8.5 kilojoules, which is not favorable. You know, we need a negative delta G naught. And so what we have to do is, we have this, delta H is 44.0, let's just do this. Delta H is 44.0 kilojoules. And then we have to figure out some temperature in which, when we multiply by 0.1189 kilojoules per mole Kelvin, we'll just do kilojoules per mole here, that this term will cancel out this. We need this term to equal negative 44. If we can get this term here to equal negative 44, then we'll have positive 44 minus, well, in other words, we need this term to equal 44. When multiplied by negative, it gives us negative 44. So the positive minus negative 44 gives us 0. And so to do this, we're going to set delta G naught at temperature T equal to 0, you know, because we want this sum to equal 0. And so we'll have delta G naught at some temperature T equals 0, which equals delta H naught at that temperature minus T delta S naught. Okay, and this is going to be about equal to delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin. And so we solve this. We add a delta T delta S to both sides and divide it. And so solving for T, we get T is equal to delta H naught at 298 Kelvin divided by delta S naught at 298 Kelvin. And so doing that, we see delta H naught is 44.0 kilojoules per mole. Delta S naught was 118.9 joules per mole Kelvin. And then we'll just multiply the top one by 1,000 joules per kilojoule, so get the units the same. And that gives us 370 Kelvin. Well, you know, that's not right, because water, the normal boiling point of water is 373 Kelvin, so we're 3 Kelvin off. But then again, we use the delta H and the delta S at 298 rather than the delta H and delta S at 373. So that error could be attributed to that. So what this means is this. If I increase the temperature to 370 Kelvin, then delta G naught is equal to 0. And so I need to go greater than that. And so if temperature is greater than 370 Kelvin, delta G naught, should be less than 0. Should go negative, because the entropy term grows bigger than the enthalpy term. There would have been an alternate method of solving this problem. The alternate method comes from this. Delta S is equal to Q reversible over T. If we restrict it, Q, then Q is just delta H over T. This is for phase transition. And this will be the temperature of the phase transition. So this will be the phase transition. This actually comes from delta S is equal to Q reversible over T. And so the temperature of the phase transition is equal to delta H of the phase transition divided by delta S of the phase transition. Unfortunately, we don't have delta H of the phase transition, because delta H of the phase transition would happen at the temperature of the phase transition. And we don't have delta S at the phase transition, so we just approximate this as equal to delta H at 298 Kelvin divided by delta S at 298 Kelvin. Under standard conditions. Here. I'll just leave it. And so it's the same equation as we just got earlier. This is for phase transition. So this is an alternate method of figuring it out. The temperature of boiling is going to be well, I can manipulate delta G, the driving force, using temperature and or non-standard conditions. So let's look at non-standard conditions. If we go to non-standard conditions, then we have two choices. We could do it at 298 Kelvin, or we could do it at some other temperature. And so let's first look at non-standard conditions at 298 Kelvin. For non-standard conditions at 298 Kelvin, we're taking our non-standard delta G, and we're going to figure it out by taking our standard delta G and adding this correction term, ln Q. Okay, right now it's non-spontaneous. So right now we got plus 8.5 kilojoules per mole. So it's non-spontaneous. under standard conditions. So what we're going to do is we're going to try to change Q, that is alter the initial concentrations or initial pressures to make it spontaneous. So alter Q to change delta G. So what I have to do is I have to figure out, is there Q here that'll make this whole second term negative 8.5? If there's a Q value that can make this term negative 8.5, then I can cancel out this, right? And then if I can make it bigger than negative 8.5, then I can actually make it spontaneous. Right? And so let's see if there's a Q value that we can determine for that. All right, and so I'm going to do this in steps. So at what Q will reaction go spontaneous? Well, if we want it to go spontaneous, then we want this term here to cancel out this term here. In other words, we want to make delta G equal 0. So we want to transition it from positive to 0 to negative, right? And so we want delta G to go through 0. Well, delta G is equal to delta G naught plus RT ln of Q. And we're going to do this at 298 Kelvin. So this is going to be at 298. This is going to be at 298. And the temperature is going to be at 298 Kelvin here. So we end up with this. We end up with delta G naught at 298 Kelvin is equal to minus RT ln. Now this is an interesting thing because if delta G is equal to 0, we call that equilibrium as well. And if we're at equilibrium, then we know that Q is equal to K at equilibrium. And so that's why I plugged in K here rather than Q, because if we're at equilibrium, that's it. And so when I'm asking you what Q will reaction go spontaneous, I can ask you what K, because it's going to be at equilibrium. So at this case, it's going to be K is equal to, well, ln of K is equal to delta G naught over RT, negative. And then we get rid of the ln by raising everything to E. So we get delta G naught over RT. So K is equal to E to the minus delta G naught over RT.
Which R value are you going to use there?
Okay, well, we'll just fill it out. And so this is going to be K at 298 Kelvin. This is going to equal minus delta G naught at 298 Kelvin over RT. We're going to figure it out by dimensional analysis. Well, what is K at 298 Kelvin? K is the equilibrium constant, so this is going to be the pressure of the H2O gas. Because Q is equal to K, Q is equal to the pressure of H2O gas. And so we're solving for the pressure of the H2O gas is going to equal E to the minus delta G. Delta G is 8.5 kilojoules per mole. R, we have to use the thermodynamic R. Thermodynamic R is 8.3145 joules per mole Kelvin. And so let's change the top to joules. So we'll go 1,000 joules per kilojoules times T, which is 298 Kelvin. So what does that come out to?
32.4 to 10 to the 2.
This is around 30 millimeters of mercury we have to do. So if we can reduce the pressure to 0.0324 bar, then spontaneous. And so what we'll do is, this is going to be a room temperature, 298 Kelvin, and we have some water here. The normal pressure, what is standard pressure? What's the normal pressure? 1 atmosphere, 1 bar. So normally there's 1 bar of pressure here. And so in order to boil the water, we need 1 bar of water pressure up. And then we get boiling, because when the vapor pressure is equal to the atmospheric pressure, boiling occurs. But what we're going to do is we're going to hook this up to a vacuum pump. When we hook this up to a vacuum, we're going to suck out the air out of here. And so that the pressure of the air that remains here, if the pressure of the air is 0.0324 bar, then we can have boiling occur. If the two pressures are equal, we'll get water to boil at room temperature. So water should boil at pressures less than 0.0324 bar. Alright, so here, this is just the first video pic, but so this is room temperature. Here's a powerful vacuum. You reduce the pressure, and then you get water to spontaneously boil at room temperature. That's a hand vacuum pump. I hadn't seen that before.
How many ways are there to boil water without using fire?
How many ways without using fire? Can you use electricity?
No.
Without using heat?
Isn't heat fire?
Well, okay, there's only one. There's one way to boil water without using any external heat. That's to reduce the pressure. You know, because we could try to change other conditions like concentration, but there's no concentration here. What's that? Yeah, this is how pressure cookers work, right? This is also refers to kinetics because, you know, if a 10 degrees C temperature increase or decrease, you know, if you increase the temperature 10 degrees C, then the cooking time is reduced. You know, it cooks much faster, and so it should cook like twice as fast. Likewise, if you reduce the temperature by 10 degrees C, then the cooking time doubles, right? So let's say I want to boil some pasta, but you know, I don't have any fire, don't have any electricity. I'm going to use a hand pump like that. I'm gonna put the pasta in that little flask and then hand pump it, and I got boiling water at room temperature. Yeah, you're gonna do that, but how long would it take to boil the pasta? Well, the instructions say it only takes 10 minutes to boil the pasta in boiling water. And so I got my boiling water there, and so only 10 minutes, it's not bad. I could save a lot of money. Don't have to use any gas or electricity. I'll just do that. But that's at room temperature. So if you boil pasta at room temperature in boiling water, how long is it going to take you? I don't know. Maybe a year or 2 years or something, because yeah, versus 373 versus 273, you know.
So is that why also cooking times vary, like with altitude?
Yeah, high altitude cooking directions, water boils at a lower temperature, right? Because you know, atmospheric pressure is less. And so if you're cooking in Denver, it's going to take a lot longer to boil pasta than if you cook it in a pressure cooker, because of the boiling point of water. Boiling point of water changes. Here, you know, here we could change the boiling point all the way to room temperature if we had enough vacuum to do it. It's good for boiling water, but it's not good for cooking, because the temperature is what's important for cooking in kinetics. Well, this brings up a point, an application of this. One application is drying things. You know, sometimes you don't want to cook it. Sometimes you want to dry things. You want to dry them rapidly. And so if you could get water to boil at room temperature, you can dry clothing at room temperature quickly by just hooking it up to a vacuum. So if you're in a rush. And this means that, well, you don't have to heat. If you don't have to heat, then you don't damage things. And so when you go into organic chemistry, a lot of organic chemicals are heat sensitive. That is, they'll start to decompose with temperature or start to burn or whatever, because a lot of organics are fuels. So you don't want to heat them too hot. And so for those types of applications, they make a special kind of oven. It's called a vacuum oven. And it's just a big box, like a vacuum chamber, with a heater inside there. And so what you can do is you can, you know, dry things rapidly at, let's say, 35 degrees C or 40 degrees C, whereas normally you'd need 110 degrees C. Like our drying ovens there, we set them to 110, 115 degrees C. But sometimes that temperature is too hot. So if we had vacuum ovens, we'd set it to like 40, 50 degrees C and dry it in the same amount of time. But we need vacuum. And so the situation here is our house vacuum strong enough to boil water at room temperature? Let's see. It turns out it's not. Maybe I should show that. I don't have a stopper, so I'm not going to show it. Our house vacuum is too weak. So what am I? Then I'm stuck to heating it to 100 degrees C? No. If I use a combination of house vacuum and heat, then I can get the water to boil at a much lower temperature than 100 degrees C. And so this is a combination, non-standard, because it's, you know, under vacuum, it's not at 1 atmosphere. And so it's going to be non-standard at some temperature T. Well, so if I want to do this under, okay, so what do you think our house vacuum is? It's not 0.03 bar. I need to go to 0.03 bar. Our house vacuum is more like 0.5 bar, like a half an atmosphere, I think. And so at what temperature will water boil? Now, what temperature will water boil at a pressure of 0.5 bar. So it's not quite enough. You know, we need the pressure to go down to 0.03 bar to boil at room temperature. So it's not quite enough to bring it down. But, you know, it's not 1 bar. 1 bar is standard. And so we're going to need less temperature. And that could be good. And so we got to look. Well, delta G under non-standard conditions at some temperature T is going to equal delta G naught under standard conditions at that temperature T plus the correction, ln of Q. So again, we want to go from a positive delta G to a negative. And so what we're going to do is we're going to set delta G at temperature T equal to 0, which is going to equal delta G naught in temperature T plus RT ln of Q. We have a problem here, and the problem is this. How can we solve for delta G naught at temperature T? You know, can we assume this? Is this assumption okay? We'll assume that delta G naught at temperature T is about equal to delta G naught at 298 Kelvin. Is that a good assumption? No, it's okay for delta H, it's okay for delta S, but it's not okay for delta G, because delta G we can change dramatically, including making it go from non-spontaneous to spontaneous or vice versa, just by using temperature. And so we can't assume that. We need the delta G naught at that temperature. If we need the delta G naught at that temperature, no problem. We can solve for that, because delta G naught at temperature T is about equal to delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin. But there's a major problem here. What's a major problem? I don't know what T is. So if I don't know what T is, then how can I solve for delta G naught at that temperature T? Right. And so it turns out we aren't out of luck, because what I can do is I can substitute this in here like this. And so we have delta G at temperature T is equal to 0, and then I'm going to substitute this up here, delta H naught at 298 Kelvin, which we know, minus T delta S naught at 298 Kelvin. We know delta S, we know delta H, plus RT ln, well, it's going to be K now because it's at equilibrium, 0. And so let's add T delta S and subtract that from both sides. Or we'll just factor out a T. If we factor out a T here, then maybe it's okay. So we're going to get delta H naught at 298 Kelvin minus T times delta S naught at 298 Kelvin plus RT, no T, sorry, plus R ln of K. And then solve this for T. So add that to both sides and get delta H naught at 298 Kelvin divided by delta S naught at 298 Kelvin plus R ln of K. Now we got it. Because now, if you look at this, we have it in terms of delta H naught at 298, which we know, delta S naught at 298, and R ln of K, where K is equal to 0.5 bar. You know, we're just saying we're going to try to keep the pressure. This is just equal to the pressure, the product of the reactant. So the product is just the pressure of the H2O gas. Right? And so, solving for T under non-standard conditions is a little bit tricky, okay? Because, for example, we saw this equation earlier. Remember this one, delta G naught is equal to minus RT ln of K. So a lot of people try to solve this. That is, T is equal to minus delta G naught over R ln of K. Does this equation work? No, this equation suffers from the same problem. We don't know what delta G naught at T is, but we can substitute it. We can just say, well, that's delta H naught minus T delta S naught over R ln of K. And then try to solve it for T. We solve this for T, we end up with this equation here. So we could have gotten the other way. Or we solve this for T, and we end up with this equation here. There are multiple ways of getting it. But we just have to be careful, because whenever we do a thermal calculation, we have to ask ourselves, are we under standard conditions or non-standard conditions? Are we at 298 Kelvin or not at 298 Kelvin? Okay, and that's going to dictate how we solve the particular problem. Not only that, you know, we have to keep track. So we plug this in, and then we could solve for the T. Can somebody solve for it? That is, T is equal to 44,000 joules per mole. This is 118.9 joules per mole Kelvin plus R, which is 8.3145 joules per mole Kelvin times ln of 0.5, which is negative 0.693. The temperature is equal to what? Hmm? 308.9?
388.9.
388.9. This is a problem. There's got to be some kind of mistake here. 468? It should be under 373. It should be between 273 and 373. People are getting this? Hmm? Yeah. All right, let me just check this calculation here.